I'm excited to introduce the next speaker, Khalilimeybodi, who is a postdoctoral fellow at the University of Virginia. He was going to talk in the session on diverse approaches to multiscale modeling, and the title of his talk is Developing Context-Specific Hypertrophy Network Identifies New Interactions in beta-adrenergic-induced hypertrophy.
Hey, everyone. Can you hear me?
Yes, we can hear you. And please share your screen.
Okay. Okay.
Go ahead.
Thank you for giving me this opportunity to present my research on the IMAG conference. Today, I want to talk about my research on developing context-specific network models that for the cardiac hypertrophy and the result of this network that can identify new interaction in each context that I focus on beta-adrenergic cardiac hypertrophy for my current research. As you know, heart is a dynamic organ in the body that grow and its shape and its mass changes during the time in response to many biochemical and biomechanical factors. And each biomechanical and biochemical factor depends on the context that the heart grows. We see the different results for the shape and the mass of the heart. If we want to divide the heart shape changes in different categories, there are three classical categories for the heart shape changes. The first one is the cardiac dilation, that it happens after, for example, myocardial infarction or when we have the volume overload in the heart. And the cardiac myocyte grows in the length more than the growth in their thickness. So we have a dilated heart. Another one is in the concentric hypertrophy, that the thickness of the heart wall grows and we have a thickened wall in the heart. And it happens, for example, when we have a patient with coronary hypertension or a problem in his or her aortic valve, like aortic valve stenosis. In this state, the thickness of the cardiac myocyte grows more than its length. And also we have a physiological type of cardiac hypertrophy that the growth is uniform and isotropic. And it happens when, for example, in the athletes with chronic exercise or in the pregnant woman. And one of the features of this physiological hypertrophy, that this hypertrophy is reversible. But for the other types, we have nearly non-reversible changes in the heart shape. And for example, for the cardiac dilation, this cardiac shape happens in most of the heart failure patients. And to understand the changing of the cardiac shape and how we distinguish between different contexts, we need to evaluate the factors that influence the growth of cardiac myocytes. For this reason, the first thing that we should focus on that is the hypertrophy signaling network that induce and stimulate the transcription factors that result in the changes in the heart, in the cardiac myocyte phenotypic or morphology changes. For the first time, our lab developed a larger scale signaling network for the cardiac hypertrophy that was developed by Royal at 2012. And for this network, we have about 17 inputs that consider different biomechanical and biochemical factors that induce cardiac hypertrophy, and we predicted the effect of these biochemical factors on the phenotypic output of the hypertrophy, like different, like variation in the cell area or changes in the transcription factors. And also, because this network is very complex and is large, and many pathway and signaling components contribute together to transduce the signal to this nucleus, there are many articles, review articles on the cardiac hypertrophy that shows that this network currently is not completely understood, and we need to focus on that to understand the cardiac hypertrophy. For making this model, we use the logic-based differential equations that uses both advantage of the logic models and ODE models, and we use a Hill function to define the interaction and the effect of any signaling component on its direct downstream component. And for modeling the interaction between different pathway and different signaling components, we use two logic and OR gate. And because our values are continuous and real values, we use this formulation for modeling the effect of AND gates or OR gates that we can see in the logic model. Based on the prediction of our model, as you can see, this model can predict the input-output data in the cardiac hypertrophy. Well, for example, that predict 109 of 114 of the outputs correctly, but this data are one class of data that we obtain from the literature. There are other class of data in the literature that are very important. For example, if we want to develop drug therapies, or for example, study the effects of different signaling components on the cardiac phenotypes, or we have, for example, an explanation for the difference between different contexts that we can see in the heart shape in the final state. As you can see, for example, for isopaternal induced hypertrophy, we can see that current model, because it's a non-specific or general model, cannot, for example, predict the effect of different component inhibition and its effect on the, for example, the output or other signaling component of the model. To resolve this problem, I developed a systematic and automated method for developing context-specific models. This method uses an automated validation core that we use signal network interaction graph, or the reactions through the predefined Excel format as input to this core. And also we use our context-specific data in another Excel predefined format as other inputs. So we have, actually we have a hybrid network inferring that we use prior knowledge network and new or perturbation data to obtain the context-specific model. Based on the interaction, based on the reactions formula and also the data, we use the NetFlux software that we developed in our lab to generate the logic-based LDE model. And based on the model that automatically generated, we simulate all of the experimental condition in our context-specific data. And finally, we obtain, for example, the validation % of the overall model for this network and this type of data. But by using the results of this automated validation, for the first step, we use the parameter estimation methods to estimate our default parameters. There are a few default parameters that we can estimate them by the data, and I can show you that this estimate of these few parameters can greatly enhance the predictive power of the model for using for the future modules. At the next step or next module, we use classified qualitative validation that shows us, for example, for different class of data, what is the performance of our module in predicting the data, and also shows us, for example, what is the limitation or in what modules of our model we need, for example, a structural or some other type of revision for our model. After that, we use the model to apply a method of context-specific global sensitivity analysis, which is a combination of deleting reaction tests and also two-step global sensitivity analysis to obtain the critical reactions that are important for the overall validity of our model. And at the final stage, we use this model to identify the missing interaction or context-specific interaction and crosstalk that can regulate the response for each context. For developing the context-specific data, we require more data than a non-specific model. In the first model, we use about 122 experimental data points that was divided in two classes, in the input, output, and input intermediate classes, from about 90 articles, that all of them are literature-based data. We expanded our data set to 450 data points that include all of the four classes, and we add in intermediate inhibition and intermediate overexpression data from about 230 articles. And this diagram shows the distribution of our data based on the agonist or based on the stimulator that results in the cardiac hypertrophy. We focus on the four main agonists of the cardiac hypertrophy: isoproterenol, angiotensin, the esterase, and phenylephrine, for predicting and developing the context-specific model for each of these agonists. As you can see, for our previous model, can predict the data, the expanded data in the two first class nearly well. For example, you can see for input, output, and input intermediate class, our previous model can predict more than 80% of the experimental data points, but it has limitation in the two new classes of data. So by estimating, using parameter estimation to estimate value of only four main parameters, the default value of four main parameters of our model, we greatly enhance the predictive power of our model for the next steps. And as you can see, for the intermediate inhibition, we have a great increase in the validation percent by just estimating four parameters of our model. In the classified qualitative validation step, as you can see, for example, for the class of input-output data, we see significant high prediction of our model to predicting the input-output relation. Also, we can see the model performance in different modules for intermediate overexpression data. Also, you can see, for example, for the class of intermediate signaling, you can see, for example, for input intermediate class of data, you can see our model can predict the data very well. The big challenge of this model in the class of inhibition, intermediate inhibition, which is that our previous model cannot predict that class at all. So, but we have so much improvement in the prediction, but there are some parts of the model that shows that, for example, this part needs, for example, a structural revision based on the model current structure for different in different contexts. As for example, we focus on the isoperturnol, we can see that CaMKII and calcineurin, the calcium downstream pathways are not very well developed in our previous model for the ISO-specific network. Okay. This deleting reaction test shows that we have, for example, this shows the specific cardiac specific network and also shows the reactions that are important, for example, for all important in all of the main contexts. For example, these reactions are important in all of the 4 contexts, but these reactions are important in the only iso-specific. This shows after applying Murray sensitivity analysis and decreasing the parameters, we show that this is the effect of total and direct effect. And also this diagram shows the main reactions in the iso-specific model. Also we have the other specific network, PE and angiotensin specific network, and we see that J-beta gamma RAS is one of the important reactions in the model. Also based on that, we add, for example, we explore all of the possible reactions as an AND gate and OR gate for between different signaling components. As you can see, for example, our model predicts that J-beta gamma RAS, combination of CaMKII and J-beta gamma RAS could be a significant improvement, can have a significant improvement in our model prediction. So we tested our model prediction, and the results show that, for example, by applying J-beta gamma, we have a little decrease in the ISO-induced ERK activity, but combination of CaMKII and J-beta gamma, we see for just only CaMKII inhibition, we have the increase in the ISO-induced ERK activity, but with combination, there is a complete inhibition of the ERK activity. Also, we see that for the calcineurin, and we validated our results because they was nearly qualitative results. We validated with using Western blot to quantitatively validate our result, and you can see, for example, for ISO combination with the CaMKII inhibition and J-beta gamma inhibition, we have significant decrease in the ISO-induced ERK activity. In the overall, we develop a systematic automated method to revise and develop context-specific large-scale signaling models with new data. We predicted and experimentally validated the effect of CaMKII in regulating ISO-induced cardiac hypertrophy through J-beta gamma. And we showed that we identified that combination of CaMKII and J-beta gamma and calcineurin and J-beta gamma synergies could be some therapy targets in cardiac hypertrophy. And I thank you, all of my colleagues and members in the cardiac system biology lab and my mentor, Dr. Jeff Sutterman, for doing this research. Thank you.